Okay, in that last segment, I got so excited about the sum and difference formulas that I didn't even get to that double angle formula. So here's the quick version of getting to the double angle formula. So we can actually then address what's going on here in this second segment, double angle formulas transitioning then to half angle formulas. So let's come back to our formulas here. And I'll just erase them and put them up on the board. And this time, I want to get right to the double angles. So here's what's going on. If we have our alpha is the same value as beta, and why don't I just call those equal to x? Each angle is the same. It could be 15 degrees plus 15 degrees. Okay? So each angle is identical. And so then if we have our sine formula, we're dealing with alpha plus beta. We're going to write that as x plus x. So in other words, we're dealing with the sine of 2x, thus a double angle. And our formula tells us that it's the sine of the first times the cosine of the second plus the cosine of the first sine of the second. These terms are commutative. In other words, the cosine of x times the sine of x is the same as the sine of x times the cosine of x. And what you observe is this term and this term are similar. So you have one term plus another identical term, and you end up with two of them. So the formula you want to memorize is the sine of twice x equals twice sine x cos x. Tuck this one into your memory banks. When I used to work in engineering, we used this formula all the time. And from this formula, it helped me remember the sum formula that we talked about a few minutes ago, sine of alpha plus beta, because what my clue was is I'm dealing with products of sine and cosine. And that helped me remember the formula that I gave you earlier. Everybody okay with this? It's not too fancy. Let's do the cosine formula, where the angles are identical. So the cosine of alpha plus beta is x plus x. So we're going to end up with a cosine of twice x, twice angle x. And that formula starts with the what? Products of cosine. So we have cosine of the first, cosine of the second. Change the plus or minus character. Minus then, subtracting, the sine of x and the sine of x again. And so what we end up with is cosine squared x minus sine squared x. A new formula. And this one, I think you can see the structure here. Product of cosines minus product of sines. Helps you memorize the cosine formula for sum and difference, or for sum and difference. Everybody okay? So it's that simple. It's not too tough. While we're at it, let me give you a couple other versions. This is the version you typically see for your double angle sine formula. Sometimes you're going to see things in trigonometry and applied science. You're going to see lots of expressions. I might as well show you this so that it's familiar. You're going to see oftentimes things like this, a sine times a cosine. If you ever see that, think back to this formula and look at what this result is. This is the same then, sine times cosine is going to be the same as the sine of twice x over 2. And what if someone asked you, sketch, what if they said sketch y equals sine x times cosine x without a calculator? If you remember the formula, sine x times cosine x is this. And this is the same as 1/2 sine of 2x, which is a sine wave with an amplitude of 1/2 instead of normally 1. And that 2 right there does what to it? Squeezes it in, makes it half as wide. So the sketch of that thing right there, of sine x times cos x, is going to be a nice sine wave, but the period is not going to be 2 pi anymore. It's only going to be pi, and the amplitude is going to be 1/2. There's a sketch of sine x times cosine x equals y. Pretty slick. Okay. Keep that in mind. You'll see this kind of thing frequently, not just in math classes, but in applying this stuff. Now, come down here for a second on this cosine double angle formula. Remember Pythagoras? Right? And we have a trig version of that Pythagorean theorem, right? Sine squared plus cos squared equals 1. So look what we could do here. Couldn't we come in here and replace this cosine squared with 1 minus sine squared? And get another version of this double angle cosine formula? So 1 minus sine squared minus another sine squared is 1 minus 2 sine squared x. I don't memorize, I mean, even after all these years, I don't memorize this thing. This is the one I remember. But if I ever see something involving something like twice sine squared or something like that, I will take this thing and I will mentally create this new formula to be able to make a replacement. You with me on the arithmetic, basic algebra here? Everybody? Ty? Okay? Okay. What else could we do instead? Couldn't we come in here and replace that sine squared term instead with, be careful of this negative in front though, the subtraction here. We could replace that sine squared with a 1 minus cosine squared, couldn't we? And so then look at what's going to happen. You're going to have cos squared x minus this expression, which turns that term positive, and we're going to end up with twice cosine squared x positive, and then minus 1 right there. And that also is equal to cosine twice x. You don't need to memorize these, but we're going to use these in the third segment, or actually in about 5 minutes probably, after I do a problem with you. We're going to use these two versions because I want to get to the half angle formulas. Do you see something related to half angles here in these formulas?
2x.
Yeah. Look, here's an angle, 2x. There's half of it right there. And similarly down here, here's an angle, 2x. There's half of it right there. So this structure right here is what's going to lead us to the half angle formulas. Okay, we'll get to those in just a second. Let's see if we can do another problem now. Okay, here's a problem out of the book. Let's come on over here. This is number 14 on page 483. It says the cosecant of theta is minus square root of 5. And it tells us also that cosine theta is less than 0. So these are the two pieces of information. And what they're asking us to find is find the sine of twice theta and the cosine of twice theta. And then also find the sine of half of theta. And the cosine of half of theta. So we got 4 problems to do here. Now, we have to have some fundamental knowledge of trig stuff to be able to, first of all, understand where this angle theta sits. There's a variety of ways of thinking your way into that. The one way, what I would suggest you do is I would first of all take a look at this cosine piece of information, thinking back to unit circle. If the cosine is negative, then you know you have to be in the quadrant 2 or quadrant 3, don't you? For that cosine reading to be less than 0. Okay, so that helps. We got it narrowed down a little bit on where theta sits. And now more particularly, over here, they told us that the cosecant of theta is negative. However, cosecant relates to sine, doesn't it, through the reciprocal. So the sine of theta, I'm just going to tuck it in up here, the sine of theta is still going to be negative, isn't it? It's just going to be the reciprocal of what you see here. So it's going to be negative 1 over square root of 5. What quadrants will theta have to be in if the sine is negative? 3 or 4. So the sine is negative on your unit circle. Those are your y readings. And so you have to be in either 3 or 4. So the combination of those two pieces of original information dictate that the angle theta must exist in quadrant 3. You then do what once you identify the quadrant? Before we start working on the actual problem here. But first, before you find the ratios, what have I emphasized since the first day in this course? Draw a picture. This is an art class. Okay, draw a third quadrant picture. Looking like this. Right? And I'm going to draw this picture looking like that with my terminal side here. So there's a picture of my angle theta. I'm going to bring it back up here to the x-axis with an x leg and a y leg shown. I'm then going to look at my ratio right here and think of this as y over r, and the y reading's negative, so I'm going to assign a negative 1 to that, and the r is going to be radical 5. And then here we are back to Pythagoras again. So 5 minus 1 is 4, square root of 4 is 2. Is that a 2 like that? Be careful, assign a negative to it because it's sitting here in the third quadrant. The coordinates of this point are going to be negative 2, negative 1. Be careful to assign the proper signs to those terms. Otherwise, the rest of it's going to be garbage. Everybody all right? Always draw the picture. Now all you'd have to do is drop things into the formula. So the sine of twice theta is going to be equal to twice the sine of theta and the cosine of theta, and you drop in your ratio values off your picture. Y over r is minus 1 over rad 5. The cosine reading is the x over r minus 2 over rad 5. Do the arithmetic and you get a positive 4 over 5. Done. That's simple. What if I got a value that was, say, 5 over 4? 5 over 4 there. Would you be concerned? Everybody should be nodding their heads up and down. Should be very concerned if you got a result for a sine reading that was bigger than 1. Sine can't get bigger than 1. I don't care what that angle is, right? So always keep your wits about you and think, does that answer make sense? Okay, let's do the cosine quickly. The cosine of twice theta is going to be the cosine squared of theta minus the sine squared of theta. And so we've grabbed the ratios off the picture again. The cosine is minus 2 over rad 5, which is going to then be squared. And we're going to subtract from it the sine readings, which is minus 1 over rad 5, quantity squared. And we get 4 minus 1 is 3 over 5, 3/5. 3/5. What quadrant does 2 theta lie in? Where is 2 theta? Look at these results. Sine of the angle 2 theta is 4/5. The cosine of 2 theta is 3/5. What quadrant does 2 theta have to lie in? Has to lie in quadrant 1, does it not? Has to lie in quadrant 1. So 2 theta is going to have to be sitting here in quadrant 1. And here's a picture of it. Where the sine of that angle is 4/5 and the cosine of the angle is 3/5. Okay. Here's another way that we can tell where 2 theta lies. We first of all earlier determined that theta was in the 3rd quadrant. So theta was trapped between 180 degrees and 270 degrees, wasn't it? Right? And what if you now double everything in this inequality? Twice theta, double this, 360, double that, 540. So 2 theta would have to be between 360, which would be here, and 540, which is, if you take 360 off of that, there's 180 right there. So twice theta would have to be trapped between here and here. Somewhere between here and here, all the way over to here. 540 would be here, 360 would be there. But you can see that by having the trig ratios here, both the sine and the cosine readings, we can determine that we're in the 1st quadrant and not possibly over in the 2nd. Okay. The mathematics is quite simple, but the trig that is the background stuff is the important thing to get to be able to handle this. All right, what I'm actually doing is I'm mixing in solving using these formulas as we're actually developing them. Are we ready to try the half angles on this problem? The sine and the cosine for half of theta? Okay. While we're at it, since we know that theta is trapped between 180 and 270, then why don't we go ahead and determine where half of theta sits? Right? We could just lay that in right here, couldn't we? And so I'm moving kind of quickly on this, so I'm just hoping you're keeping up with the flow. If I took half of theta in this inequality, then that means half of theta is going to be trapped between 90 and 135, right? Okay? So just keep that in mind. Keep that in mind. all I did is just divided everything in the inequality by 2. 90, theta over 2, half of 270, 135. Okay. So let me come back over to this first board here. And let's go right up here on the top, since what we want to use is this double angle formula here. So the information they gave us was regarding angle theta. So if we come down here and look at this second, here's the double angle formula for cosine. If we use the Pythagorean identity, we can rebuild it this way. And I think you can see right here that the sine of theta could be solved for. We could solve for the sine of theta right there. So if we start with 1 minus twice sine squared x equals cosine twice x, we could solve this for sine x. So let's go ahead and do that. So if we subtract 1 from both sides, we're going to get cosine of twice x minus 1 equals this negative twice sine squared x. If we then divide both sides by negative 2, we can change the signs of the terms on the right side then, because we're dividing by negative 2. And so I'll turn those terms around, and we'll have a 2 denominator. So we're going to get sine squared x equals 1 minus cosine twice x all over 2. Okay? Everybody feeling okay with this? Any questions? All I'm doing is moving things around on that formula. Okay. Now, the problem we were asked to find was the sine of theta over 2. So if I let x equal theta over 2, then the sine squared of that theta over 2 angle is going to be equal to 1 minus the cosine of, what's 2x? Look right here. 2x equals theta. So 1 minus cosine theta divided by 2. Just a substitution. The thing you want to remember when you see a formula like this is you don't have to be using symbols x like this. You can have, all you have to observe is that this value right here is half of that. And so here's another way you oftentimes will see that formula written. This angle is half of that angle. Thus, it's called a half angle formula. Now, to solve for the sine theta in this particular problem, you're going to have to take the square root of both sides, aren't you? So, for the particular problem, and I want to leave a little space here because I want to play with this formula a little more in a couple minutes. But for the particular problem we're doing now, we want the sine of theta over 2, and that's going to be plus or minus the square root of 1 minus the cosine of theta over 2 inside the radical. Feeling good? Okay. Now, let's go ahead and drop in the numbers. So the sine of theta over 2 is going to be equal to, I'm going to worry about the plus or minus in just a moment, but let's come inside here, 1 minus, and we have to look back at our earlier work. The cosine of theta we had determined previously was, I believe, minus 2 over radical 5. And that goes into that numerator right there inside the radical. And I think you can see why a couple of sessions ago I took you folks clear back to arithmetic with fractions, cleaning up complex fractions and stuff. Because if you were rusty on them back then and I hadn't explained that technique for cleaning these things up, it would be really a mess for you here, where you got this complex fraction inside the radical. Is everybody okay with the math? Now, this is just plug and chug, right? Just drop things in and crank out the arithmetic. But you also have to use your brain here, because look at this. You have to make a decision about which do you select, positive value for this sine reading or negative value for this sine reading. So you have to go back to the earlier work we did where we took and determined we had theta tucked into the third quadrant between 180 degrees and 270 degrees, and then we need to find out where this theta over 2 angle sits so we can select the appropriate plus or minus right here in front of the radical. So we did that work earlier. This is trapped, the angle theta over 2 is trapped between 90 degrees and 135 degrees. So therefore, this is the math symbol we use for therefore, shorthand. Therefore, the sine is what? Sine of theta over 2 is greater than 0, isn't it? It's in the second quadrant, actually in a particular spot in the second quadrant. And so we're going to select a positive right there. I usually will write that down and circle it. And then if I look back at this later, it means I thought about it, okay, instead of blindly believing it. Okay, and then we're going to clean that up. So we're going to have the sine of theta over 2 is equal to the positive radical. And what are we going to do inside here? Multiply top and bottom by what? Radical 5, right? The common denominator of all these fractions inside there is radical 5. So multiplying the top and bottom by radical 5, I'm going to get radical 5 times 1 plus 2 over 2 radical 5 inside the radical. This is really rad. Okay. Uh-oh, might confuse that with radians. We don't want to do that. Okay. There's strange humor in math and engineering, so it gets stranger the further you go. And so then we're probably going to want to rationalize that denominator inside there by multiplying top and bottom by rad 5, still inside the radical. And tidy this up, one big radical, and we're going to get 5 plus 2 radical 5 over 2 times 5 is 10. There's our answer. Where do you think trig students have the most trouble? Arithmetic. Right here. Right there. Okay. So this is the course, as I said earlier, where you get good with fractions, you get good with arithmetic, and it also really tunes up your algebra skills. Could we find the cosine reading for half the angle? Might as well. Okay, which formula are you going to use for the cosine of the half angle? Which formula? This one? No. This one? For the cosine? No. This one, because it's sitting right there. Okay. So let's take a minute to do that. You still awake? Okay. Yeah.
You picked that one because it only had sine or cosine in it?
Yes, because what I'm trying to find, I'm thinking, okay, I know where this formula is going to take us. We're going to solve this thing just like we did the other one. Just like we solved this one for sine squared. We're going to solve this one for cos squared. And then the other side of that equation is going to involve the cosine of twice that angle, which is our theta. That's our theta, which we know about. So I'm not going to erase all of this. We took care of the double angle stuff already. So what we're doing now is we're again letting x be equal to our theta over 2. So our theta is twice x. And the formula we're using is the cosine of twice x equals that thing at the bottom there, twice cosine squared x minus 1. So when I move the 1 over to the other side, I get cosine twice x plus 1 equals twice cos squared x. And I solve that for cosine squared x. And it's equal to, typically it's written 1 plus cosine twice x over 2, the common denominator 2. And then we make our substitution from here into this. So the cosine squared of half the angle is equal to 1 plus the cosine of our angle theta over 2. Square rooting both sides. The cosine of our theta over 2 angle is going to be plus or minus the radical of 1 plus cosine theta over 2. Dropping in the ratio from the previous work, the cosine reading again was negative 2 over radical 5 for the cosine reading inside there. And so we have the radical of 1 plus the the negative 2 over radical 5 divided by the 2. And we need to choose the plus or the minus for where the half angle sits. The half angle work we did earlier, it's over here on the right. The angle sitting between theta over 2 is sitting between 90 and 135 degrees. So we have to select what here? Negative. We select negative for that cosine reading for the half angle. And then look at the math here versus the math that we did back on the earlier board. Is there any difference? The only difference is what?
The sign.
The plus or minus character inside that radical. So if you don't have that previous board sitting in front of you, all you have to do is the problem we did previously. There was a negative sign right here, and our sine and cosine both happen to have been negative in this problem. So this result's just going to change and become a negative compared to the other answer. So we're going to end up with the negative of the radical of 5 minus 2 radical 5 over the common 10. Okay. Any questions on the math on this process? It's probably more than half arithmetic, but you also have to, it's critical that you draw the sketches. And I don't know that the textbooks typically emphasize that as much as I do, but I think it's absolutely critical because you can catch mistakes that way. Okay, let's end this segment, and then we'll get on to segment 3, and we'll see a couple new interesting things in the last segment. Okay. Anybody have a